Hi, I'm Orion, and today I'll be presenting the vast potential of memristive processing in memory for accelerating the fundamental matrix operations of matrix multiplication and matrix convolution. Let's begin with some background on processing in memory. Traditional computer systems separate computation and storage into the individual CPU and memory units. Thus, if we have data in the memory that we want to process, we have to take the data from the memory, bring it to the CPU, process it in the CPU, and then write it back to the memory. Now initially this separation made sense, but in recent years the data transfer between the CPU and the memory has become orders of magnitude more expensive than the computation itself. That is, the vast majority of energy and latency is spent only on transferring data from one side of the chip to the other. Thus, processing in memory solutions aim to integrate logic functionality within the memory. So instead of having to send the data from the memory to the CPU and back, the CPU could simply send a logic operation request for the memory to perform logic inside the memory on data stored in the memory with the result remaining in the memory. The question is, how do we implement such a memory that is capable of inherently performing both memory and logic functionality? One example is that of digital memristive processing in memory. It all comes back to the memristor. At first sight, it's like a resistor in that it has two terminals and it has an internal resistance. But it also has a highly unique property. When you pass a current through the memristor in one direction, the resistance of the memristor increases, and when you pass a current in the other direction, the resistance of the memristor decreases. We can already use this to store binary information. Let's classify the possible resistance values into either a logical 0 or a logical 1. And then we can write a resistance value to the memristor with a high current, and we can read from the memristor by putting a low voltage, measuring the current, and then deriving the resistance. So that means that a single memristor can store a single bit of data. Can we also use memristors for logic? Well, consider this circuit here on the left, where we have three memristors connected, and we're applying a fixed voltage at the top and the bottom, for example, 1 volt and 0 volts. Due to the inherent voltage divider structure that forms in the circuit, we actually find that the resistance of the bottom memristor will change to be something that is conditional on the resistances of the top two memristors. For example, the bottom memristor will have a state corresponding to the NOR of the resistance states of the top two memristors. Essentially, we performed a basic logic gate using the memristors themselves in the resistance domain by simply applying fixed voltages at the top and the bottom. If we look at the circuit, inside a crossbar array of memristors, that is vertical bit lines and horizontal word lines, then we can actually see that the circuit exists within a single row. If we apply voltages on certain columns of the crossbar, then we get that within one row we have a NOR gate from two memristors that are input into a third memristor that's the output. Not only that, we notice that by applying the voltages on the bit lines, we get a NOR gate in every single row of the crossbar. And they all happen in parallel. Essentially, every row performs its own NOR gate in parallel to all other rows. We can use this in an abstract model. First, think of the crossbar as a binary matrix of information because every memristor stores a single bit. And now we can express these operations as taking two arbitrary columns, computing their bitwise NOR, and then storing it in a third column. All of this happens in a single cycle because all we had to do was apply the voltages on the bit lines, and the memristors perform the computation by themselves. So we have operations on columns with order of 1 time complexity, and we can actually also get order of 1 time complexity for row operations by applying voltages on word lines instead of bit lines. We can start to improve this. For example, if we add partitions, that is, we separate parts of the crossbar using transistors to enable independent units or independent partitions, then we can get multiple row or column operations per cycle, all within the same crossbar. Also, if we have many crossbars, as is typical in a regular memory, then all of the crossbars can operate at the same time because we can simply share the instruction. That is, send the same instruction to multiple crossbars, and because there isn't any shared unit for computation, everything happens in a distributed manner in all crossbars with full parallelism. Okay. So we have massive parallelism for basic logic gates, such as NOT, NOR, NAND, or OR. What can we do with it? Well, first of all, logic gates that are functionally complete can give us arithmetic in the form of addition, multiplication, division. And if we have arithmetic, then we can start to talk about applications. For example, in this work, we'll talk about matrix multiplication and 2D convolution, but from there you can continue to generalize, for example, to deep neural networks. And the entire time, we're using the massive parallelism that we have from basic logic gates to expand to high throughput arithmetic and applications. Let's begin by deriving high throughput arithmetic from our massive parallelism. Let's assume that we have two vectors of, for example, 1024 elements, where every element is a 32-bit integer or floating point number. We want to add those two vectors. And let's say that the vectors are stored in a crossbar, where for every row we have one element from each vector. What we can do is a bit serial element parallel approach. We look at the NOR gates that construct a 32-bit adder, and for every NOR gate in such an adder, we perform a column operation across all of the rows. That gives us parallelism across all rows, meaning that at the same time that we compute the addition in one row, we're computing the addition in all of the rows. That means that the latency of the addition isn't even dependent on the vector dimension. It's dependent on the representation size, on 32. We can actually even improve this even more by using partitions for a bit parallel element parallel approach. This means that we're both working on all rows simultaneously, and for every row we're also performing multiple NOR gates at once. This reduces the constant even further, giving us massive throughput and low latency for in-memory arithmetic. Now that we have arithmetic, let's begin with one of the most fundamental matrix operations, which is matrix vector multiplication. Let's assume that we're given a matrix A of 1024 rows by 8 columns and a vector X of 8 elements, where every element is a 32-bit fixed point or floating point number. Now assume that the matrices are stored as we see here, where every element is stored horizontally, meaning that we occupy 32 horizontal memristors for every element. The basic idea for this matrix multiplication starts by taking X and duplicating it across all rows. And then we compute an element parallel inner product, where essentially every row takes its row from A and its copy of X, computes their inner product, and stores it as the number at the end. Now overall, we've essentially computed here the output. The vector matrix multiplication, A times X, is stored exactly here at the end of the crossbar. That is, we've been able to compute the matrix vector multiplication with massive parallelism throughout by using our high throughput arithmetic. But there is a downside to this technique. Because we store numbers horizontally, always using 32 horizontal memristors, we're restricted to very asymmetric sizes for our matrices. For example, 1024 by 8 columns. And these are sizes that are not very typical. So in this work, we start by using theory of block matrix multiplication to address this concern. Assume that we take A and split it into a left half and a right half, and also take X and split it into a top half and a bottom half. Block matrix multiplication says that we can actually compute the matrix vector multiplication of A and X by computing, first of all, the smaller matrix vector multiplications of A1, X1, and A2, X2, and then computing the sum. Let's try to use this idea to tackle a more symmetric matrix vector multiplication. For example, when A is 512 rows, but 16 columns, instead of 1024 by 8. We take the left half of A, store it at the top, and then we take the right half of A and actually store it underneath it. And we do the same thing with vector X, splitting it into some part that's stored at the top and the other part that's stored at the bottom. We continue like before, duplicating X across all the rows, and then again we perform an element parallel dot product, which essentially gives us both A1, X1 and A2, X2. All that's left is to add these two results, so we start by shifting A2, X2 to the right and upwards, using only row and column operations, and then we add the two results using an element parallel adder. Overall, we were able to compute the matrix vector multiplication of A and X, even though A had 16 columns. And we can actually extend this idea to many more dimensions, for example 256 by 32 or 128 by 64, and now we're getting much more practical dimensions that could be used in real-world applications. Let's shift to discussing convolution, another fundamental matrix operation. For convolution, we want to take an input matrix A and apply the convolution with some smaller matrix K, the kernel. Now the problem with convolution is that inherently you have more complex operations that might require shift. For example, you need to take the kernel and shift it around so that it can multiply every element in A. Previous ideas for trying to implement in-memory convolution can be split into two different concepts. One is to insert shifters into the crossbar architecture so that they can move the wires physically. But the problem here is that you're adding additional periphery that can complicate the crossbar itself. The other option is to take the kernel and to duplicate it into multiple locations and to start shifting it around, multiplying by elements from the input matrix and computing the output. The problem with this concept was that you require many internal shift operations, which are not external shifters. They're shift operations using row and column operations, but that can lead to a very high latency overhead. Instead, we're going to try a completely different approach that we call input parallel convolution. Usually you look at a single element in the output and figure out how to compute that element in parallel. But instead we'll look at a single element in the input and ask what elements in the output does this input element contribute to. By looking at it from that perspective, we can get to this expression, where the matrix convolution of A and K is expressed as the weighted sum of shifted versions of A by weights from K. For example, start by taking all of A and multiplying it by the top left element in K. Then take all of A but shifted leftwards, multiplied by the next element in K, and so on. This idea is much more easy to parallelize because we're always taking an entire matrix and multiplying it by a single element. And also the shift operations are much simpler because we're shifting the entire matrix at a time. Let's look more in depth into the algorithm itself. We start by having A and K stored inside the crossbar and initializing some output. At first, we just want to multiply A by the top element in K, that is the green element in this case. So we go column by column, starting with the first column, multiplying the column from A and the element from K, and then continuing until the last column, where we compute the entire product of A and that element. Then we move on to the next element from K, and we actually access the columns of A shifted. Instead of having to shift A horizontally, we merely access the columns shifted and now perform a multiply and accumulate, again for every single column in the output. Now that we're moving on to the next element from K that comes from a different row, we first have to shift A upwards. After we've shifted A vertically, now we can go back to having the elements from that row of the kernel and computing the product of A and that element. Again, we go one column at a time for every element in K, and then we can go for the last element in K where we both have A shifted upwards and we start from the second column onwards. We've now computed the convolution of A and K using element parallel operations for everything, and with very efficient shifting. Let's move on to evaluation. Our evaluation methodology involves a cycle-accurate simulator. The basic idea is that we take our algorithm, we implement it in NOR gates, and then we have a simulator that simulates the logical interface of memory. The simulator receives NOR instructions from the algorithm, performs them blindly, and at the end, after performing all the NOR gates, we check to see if the output that was computed is the desired result. Using this simulator, we're able to start by demonstrating the results for matrix multiplication. We see that at the asymmetric dimension of 1024 by 8, we match the results from the previous papers, but we're also able to extend to much more practical dimensions, such as 128 by 64. If we look at matrix convolution, then we see that even for the small unrealistic example of 1024 by 4, we're able to improve the latency by over 2x because we're doing more efficient shift operations. And then we're also able to generalize to much more symmetric dimensions, like matrices A of 128 by 64. Essentially, we're getting both faster and more practical convolution. In conclusion, we started by talking about Memristive PIM and the massive throughput that it provides for arithmetic. Then we use that throughput to get efficient and flexible matrix vector multiplication with very practical dimensions. And now we talked about convolution, a task that is much more difficult, and yet we're able to implement it with full parallelism because of an input parallel approach that gives us something that's both efficient and again flexible in dimensions. And now overall, these fundamental operations can provide huge potential for new PIM applications. Thank you for listening.